Welcome everybody to a new session of the Young Machine Learning Needs Mathematical Optimization seminar series. Today we have the pleasure of having these three speakers, and as usual we will place the question till the end for the three of them. Sorry. And now Sinia is going to present them.
Yeah, so thank you, Christina. Our first speaker is Remedios Sillero-Denamiel, sorry for my pronunciation, and she's a postdoctoral researcher at School of Computer Science and Statistics in the Trinity College, Dublin. So, Remy, floor is yours. You have around 20 minutes.
Okay. Can you hear me?
Yes, everything is great.
Okay, perfect. So thanks, Sinia, for the introduction, and thanks, Sinia, Cristina, Dolores, and Emilio for organizing this online seminar series. And of course, thanks everyone for coming. Well, in this talk, I'm going to present a work entitled On Linear Regression Models with Hierarchical Categorical Variables. This is a joint work with Emilio Carrizosa from the University of Seville, Laus Mortensen from the University of Copenhagen and from Denmark Statistic also, and Dolores Romero Morales from the Copenhagen Business School.
Sorry, Reme, we cannot hear you.
Oh, sorry, now?
Now, yeah.
Okay, so, well, in this work, we are interested in linear regression models for a continuous response variable y, and we are going to consider that in our set of predictors variable, we have continuous predictors as well as dummy variables, and they are called like x prime. And in addition, we are going to consider that we have a special case of categorical predictor variables, which are such categorical predictors that have a hierarchical structure in their categories. Okay, so the first part of the model is related to the continuous and dummy variables, and the last part would be the part of the model regarding the hierarchical categorical variables. Okay, so this kind of variables, the hierarchical categorical variables, appear in different fields of research. One example could be the spatial statistics with the nested spatial data, and an example could be the European Union with the nomenclature of territorial units for statistics, where the small regions are consolidated at basic regions, and these in turn are consolidated at major socioeconomic regions. Other example could be in retail business analytics, since each retail chain maintains a product hierarchy, which is necessary to conduct business processes such as store replacements. Or, for instance, in official statistics, with the economic activity data, where the interdependency of activities form a hierarchy also. Okay, in order to visualize, better visualize this kind of variables, here we have an example. We consider the variable geography for the US, and well, this variable can be coded by using the 51 states, which is the highest level of granularity for coding this hierarchical categorical variable, or instead we can use the subregions information, which is Pacific, mountain, and so on. And in this case, we can use only 9 categories, or even use the region information, and then only 4 categories is used to code these variables. And this is the least granular representation of geography. Okay, so in this paper we consider the tree representation for this kind of categorical variables. Then for each hierarchical categorical variable j, we consider a directed tree tj, which has a root r. Then v denotes the set of nodes in the tree, and L denotes the set of leaf nodes. In the previous example, the set of leaf nodes would be the 51 states. Okay. And we have to introduce also a notation for the path from the leaf node L to the roots of the tree, which is the set of categories of nodes associated with the unique path in the tree from such leaf node to the roots. An example could be, for instance, if we consider the leaf nodes Washington, the path associated or with such a leaf node would be US, West, Pacific, and Washington. Okay, and we build a path for each leaf node in the tree. So, given this notation, now I'm trying to explain what is the main goal of this work. Well, if we build a linear regression model, the variable geography, for instance, has associated 51 coefficients in the model. Okay, so we wonder if it's possible to fuse some categories, which implies reduce the complexity of the variable in the model, but without harming much the accuracy. Okay, and we can use the hierarchical structure of the categories to do it. For instance, if the states in East South Central are homogeneous, maybe we can include all such states in the subregion information and only consider such in our model. Then in this work, we propose a mathematical optimization model that trades off the accuracy of the linear regression model and its complexity. And the complexity is measured as a cost function of the level of granularity used for the representation of the hierarchical categorical variables in the data sets. Some advantages of this goal. Well, the first would be the interpretability of the model, because a figure number of coefficient has to be estimated. Also, we can reduce the parameter estimation error for the same reason. And other advantages could be, for instance, in this example, that we can reduce the data gathering cost. Because maybe we only need samples from the subregions, but not from each state of the subregion. So it can be reduced. Or if we take into account data privacy consideration, because it's not the same to give the state information than only the subregion or the region one. Okay, so no. Yeah, so well, reducing the complexity of the linear regression model boils down to choosing a subtree Sj of the original tree Tj for its hierarchical categorical variable. So we want to measure the mean square error associated with such subtree and we measure it's like as usual in linear regression models. The first part, the tilde part, is related to the non-hierarchical categorical variables, and the last part of the formula is related to the hierarchical categorical ones. And in order to measure the complexity of such reduced linear regression model, we calculate this addition where CJL is the cost associated to the leaf node L in the tree representation for the hierarchical categorical variable J. Okay, so we calculate this in this way, the complexity of such representation. Then the problem that we want to solve is a bijective problem. We want to minimize the accuracy and the complexity, the number of coefficients in the model at the end. So in order to solve this problem, we present a collection of constraint problems, and we want to minimize the mean square error subject to the complexity of the model is bounded. Okay, and this C can be given by the user as the cost associated to each node, or in the numerical example we fix this C in order to solve a real example. So later we will see an example of such value. Then we propose a mixed integer convex nonlinear formulation to solve this idea. We want to minimize, as I said, the mean square error, and we impose some constraints in order to include the hierarchical structure of the variable in the model. The first set of constraints model that only one node is selected per path, becoming thus a leaf node of the subtree SOT. Okay, the second set of constraints impose that the threshold C on the complexity of the reduced linear regression model. And the last part of the formulation these constraints impose the range of the decision variables. Okay. And well, note that in the last part of the objective function, we have semi-continuous variables. Z is 0, 1, and beta is continuous. And well, in order to solve this, we use big M constraints. Then, in order to illustrate how our methodology works, we are going to consider this real-life dataset, CancerReg. This dataset aims to predict the continuous variable Y, which is the mean per capita cancer mortality. It has 31 non-hierarchical categorical variables, and only, well, the geography variable, which is the hierarchical categorical. And in this example, we are going to fix the costs associated to each node in the tree equal to 1, which means that at the end we want to minimize the number of coefficients associated with the hierarchical categorical variable geography in the model. Okay, and we solve the value, the C value is in this set. We set C from 1 to 51, which is the number of coefficient, the possible coefficient associated to the hierarchical categorical variable. Solving that, we obtain the Pareto frontier, this one. The x-axis show the mean square error associated to its reduced linear regression model, and the y-axis show the number of coefficients associated to such a hierarchical categorical variable in the model. If we consider, for instance, these three red points. The first one is related to this subtree representation for the geography variable, and here we consider 44 categories. We can see that the mean square error associated to such reduced linear regression model is 0.408. And if we reduce the categories by half, 21 in this case, and this representation of the variable geography, we obtain a good mean square error as well. It's very close to the previous one. Or even with only 14 categories, the mean square error is still good. So with this example, we can see that much less granular representations can be found at the expense of slightly damaging the accuracy. So we, as conclusion, or to conclude, here we present a new methodology to deal with a special case of categorical variables, hierarchical categorical variables in regression models, and we propose a mixed integer convex quadratic problem with linear constraint to trade off the accuracy and the complexity of the model. Some extension of this work could be when we deal with a large number of categories, instead of considering all the categories at once, we can perform a sequential pruning, or even try to cluster the categories based on a dissimilarity measure in order to have a fewer number of categories for each hierarchical categorical variable at the beginning of the model. And well, I have to say that we have applied this methodology for the objective function of the OLS model, but we can change it, and for instance, for the sake of dealing with strongly correlated non-hierarchical predictors, we can use the objective function of the elastic nets, or even by that of the lasso and its variants, to also get sparse solution in terms of non-hierarchical predictors. Okay, well, this work is on ResearchGate, so you can find the full PDF there. And well, here you have some references, and my email, and all the research grants and projects that has support this research. And thank you very much for your attention.
Thank you very much, Remy. So I think we leave questions till the end. So yeah, so I'm going to present the next speaker. Our second speaker is Manuel Navarro Garcia. Manuel is a PhD student at Universidad de Madrid from Spain. And Manuel, please, floor is yours. And we
okay, hello, can you hear me?
Yes, everything is fine.
Okay, so I'm Manuel Navarro Garcia. I'm a PhD candidate on the University Carlos III de Madrid, as you say, and working together with Comborevi AI Technologies, that it's a startup focused on data science and machine learning. And today I'm going to present here a work that I've done joined with Vanessa Guerrero and Maria Durban, called Mathematical Optimization Approach to Constraint Smoothing and Out-of-Rate Prediction. So, in many research areas, we want to study the relationship between a continuous predictor and a response variable, and here smoothing plays a leading role because it reduces noise, so it allows us to detect patterns, it predicts trends on the data like seasonality, but also interpolate missing values in the region where we feed the data. However, in many situations, we need to impose additional shape requirements to these curves, such as controlling the sign of the curve, for example, to be non-negative or non-positive, or in any derivative of the curve, for setting values that the curve of any derivative must attain, for example, to impose that the growth rate of the curve at a certain point have to be above a certain threshold, or when we have group data, we want to monitor the interaction between these curves. Of course, these requirements has to be met in the observed domain and out of range prediction. So I'm going to present here two motivational examples. The first one is the evolution of number of fatalities in Spanish regions published by El País, which is a Spanish newspaper, last October. And we can see in the first row, the third picture in Aragon, that although all the values, the observed values are non-negative because it's the number of fatalities, the curve attains negative values, and this is not acceptable. Another motivating example can be forecasting mortality rates. Here we have the mortality rates for different ages, mortality rates at the the number of deaths scaled by the size of the population, and we want that larger mortality rates correspond to older ages. But when we make the forecast, we see that the mortality curve of the 69 years old crosses the one of the 68 years old, and this is not biologically acceptable. So in this work, we address the problem of constrained smoothing and out-of-range prediction in the context of univariate regression with continuous predictors, combining two paradigms. First, additive models, in particular P-splines, used to estimate the function, and semi-definite programming used to handle the non-negativity constraints. So first, what are P-splines? In P-splines, we will assume that the unknown function we want to estimate is approximated by this linear combination of real coefficients Aj and a B-spline basis of cubic B-splines over a certain knot sequence, which is a non-decreasing real sequence. And we can see here a B-spline basis with evenly spaced knots that the position of the knots are in the vertical lines. And for example, if we fix here on the red B-spline in this element of the basis, this is a piecewise cubic polynomial function with join in a differentiable way. And as we can see here, they are boundary supported. So imagine that we have gathered n realization of the sample and we order the sample in a non-decreasing way. The question is how many knots we use to define the knot sequence, and the more difficult task, where do we locate them? P-spline takes evenly spaced knot sequences ranging from 1 to k plus 7. I will enter in this in a moment, where k is the number of intervals in which the domain of the data is split, and we choose this k much lower than the number of the observation. And we set that the first, the fourth knot corresponds to the minimum value of the regressor vector, and the k plus fourth knot to the maximum of this regressor vector. Why to choose k plus 7 and not k plus 1 knots? Well, if we choose k plus 1 knots, we will end in the left image, where not all the P-spline bases have the same shape, and we will have to put different weights in the P-spline bases. If we choose to put 3 knots at the left and 3 knots at the right, and 3 because we are using cubic B-splines, all the bases in the fitting region will be the same. That it's free computationally speaking, and we will do that to avoid undesired edge effects. So The coefficients AJ we want to estimate are solved with this objective function that has two terms. The left term is the least square criterion, and the right term it's composed by a smoothing parameter greater or equal to 0 that needs to be 2. This is the price we pay for evenly spaced nodes times a discrete penalty or second order penalty that approximates the second derivative of the curve. To gain a little insight of this objective function, let's set some values of lambda. If lambda equals to 0, we will have the least square criterion, so we will overfit the data in most of the cases. And when lambda tends to infinity, we will need that the second term it's equal to 0 to minimize the objective function. So the second derivative of the curve will be 0, and we will end up with a line. That is to say, the least possible wiggly curve, and we will, in most of the cases, underestimate the data. Here we can see in the upper figure, when lambda is equal to 0 with no penalty, that we are overestimating the data, and when we impose this penalty and choose a right lambda parameter, then the result is pretty good. So, what if we want to forecast, predict new values outside of the range we gather the data? For example, imagine that we have some predictor values to the right of the fitting region we defined previously. We can extend the node sequence that we defined before by adding some extra node that has to have the same step length as before, and we will add nodes until the new fitting region is inside of in the range of the node sequences. Here we have an extended B-spline basis where the red vertical line is the end of the fitting region, and we complete in solid gray lines the B-splines that we started before, and if necessary we construct new ones, and as we can see in dashed black lines. And how predicted values should be treated in this setting? We will follow the same approach as Curry and Carballo by treating the values to be predicted at missing values. That is to say, we will assign a 0 weight to the missing values and a weight equal to 1 to the values that were observed. So we will end up with a very, very similar objective function with two main differences. That now we will have more nodes, and we will have to implement these weights here in the first part. So now we have to impose the constraints. Let's review the state-of-the-art of non-negative constrained P-splines. The first naive approach we can take is to constrain the coefficients Ij we want to estimate to be non-negative, because P-splines were non-negative, so this linear combination will be non-negative. But it's pretty simple. Some researchers impose sufficient but not necessary condition on higher derivatives. For example, Boyers and P and Wood made a reparameterization of the basis and the penalty terms. And Meyer used a weighted projection onto the polyhedral convex cone, and she attains equivalent relation for certain degrees of the basis. On the mathematical optimization framework, Monteiro et al. Developed a quadratic programming and semi-definite programming approaches, but smoothness in this case depends on the number of the position of the nodes. And after that, Papa and Alizadeh, and Shea and Alizadeh, developed a semi-definite programming formulation with non-negative p-splines, but with these undesired edge effects we described before. And to our knowledge, no previous work in the literature was able to solve the problem of constrained out-of-range prediction. So, how can we characterize non-negativity? Well, we know that if we have a polynomial that is of even degree, this polynomial will be non-negative if and only if, this is an equivalence relation, if there exists a semi-definite matrix such that we have this relation. And this, using some range of variables, was developed in Bersimas and Popescu. So arbitrary polynomial, it doesn't matter if it's now of even degree or not, it's non-negative in a finite interval if and only if there exists a semi-definite positive metric such that we have these equations. On the left part of the equations, we have the sum of some elements of the semi-definite matrices, and on the right side, we have either 0 or either a product of the coefficients of the polynomial and some weights. So, recall that at every interval, we have 4 p-spline bases that are non-zero, as we can see here in the central interval. And each of them, it's a cubic polynomial, as it has the form of this with j as the coefficients. Then the function to estimate will be a cubic polynomial of this form. Then we can estimate the non-negative smoothing p-splines as this semi-definite problem with a quadratic objective function, where this W has the weights of the Bersimas and Popescu theorem. J corresponds to the coefficients itself of the basis, and the matrices H are auxiliary matrices to have the left-hand sides of the inequalities. The forecasting framework is really similar. We substitute here the objective function by the out of prediction objective function, and then we have to extend this to all the new nodes. This can be extended to a large variety of problems. For example, non-positivity, or the function to be estimated to be above or below a fixed threshold, but also on the derivatives, because p-splines are differentiable, so we can derivate this unknown function. So non-decreasing, convexity are examples of a constraint that we can derive from here. But also in group data, imagine that we have G curves that we want to estimate simultaneously belonging to different groups, and we want that these curves do not overlap. Well, we can constrain that the difference of consecutive curves are non-negative. Let's see some numerical examples. All the optimization models will run with Mosaic under Python, and Lambda was chosen as the minimizer of the generalized cross-validation criteria. For example, in this simulated example, the black curve we see here is non-negative, but when it's added to some Gaussian noise, we see that the constrained fitting curve, the green one, is negative near 125. However, when we impose non-negativity over all the intervals, we see that this constraint avoids the curve to be negative at any point. In the previous example we have seen before of forecasting mortality rates, we see that if we impose that the curves cannot cross over, we see that now the curves cannot cross over neither in the fitting region nor in the forecasting region. And now to finally address the problem of the COVID number of infections, we can impose non-negativity both in the fitting region and in the forecasting region and predict, for example, imagine that we have seen an increase in the number of infections and we have the information of the first wave. We can set a number, a range of models to implement the information on the first wave to the second. For example, if we don't add any information, we will have the blue line. If we set that the derivatives on the second wave will be double the first wave, we will have the brown one. The pink one will be the derivatives double the first wave and adding a 1 day time lag, and the green one it's for illustrative purposes only. So, conclusions. The problem of estimating a small curves in the univariate regression, satisfying certain requirements about the sign monotonicity curves on relative position, has been successfully addressed for an arbitrary degree of the basis. An approach based on p-spline estimation under a semi-definite programming mathematical optimization approach has been developed. Our methodology is suitable for constrained out-of-range prediction for the first time, as the authors are aware, and this framework is flexible to incorporate user knowledge. And what's next in the ongoing work? Well, multiple regression model. However, as Hilbert himself asked, it is not possible to know if a given multivariate polynomial that is non-negative over the real numbers can be represented as a sum of squares and semi-definite matrices on rational functions. Our approach consists of imposing the constraint just on a finite set of curves. For example, in this picture, on the red curves of the surface. So we are extending this m-dimensional surface, that is to say, to multiple regression models which satisfy shape constraints. We are preparing a public library in Python that will include all the examples and implementations in the multidimensional framework, that I hope that the first version will be out very, very soon. And in the future world, we can incorporate variable selection, if we have multiple variables, or exploring other loss criteria or non-Gaussian errors. And that's all. This is the references I added in the presentation. And here I encourage you to look at the preprint in ResearchGate of our work. Thank you.
Thank you, Manuel, for your great talk. So we, as before, leave questions to the end. And now it's time for our third speaker, James Fitzpatrick. I hope I pronounced it correctly. James is a PhD student at Quinn School of Business, University College, Dublin in Ireland. And please, James, floor is yours.
Thank you. Okay, so yeah, hi, my name is James. I'm supervised by Dr. Paula Carl and Dr. Deepak Ajwani, also from University College Dublin. And I'm just going to give a quick overview of the work that I did relating to our approach to using machine learning to help us solve the traveling salesman problem. So if I can figure out how to move to the next slide. Yep. So basically, the contributions of this work that we did were in particular to take supervised learning models and use them to help us reduce traveling salesman problem instances, and I'll explain exactly what that means in a second. We did this by expanding on previous works to get us better results in terms of problem reduction, and also to provide optimality guarantees on those reduced problem instances in terms of what we can do when we try to solve them. We propose new features that are cheap to compute, cheap and easy to compute, and we show that when we actually try to use this in practice, we can reduce the difficulty of our problems, or rather we can reduce the number of variables in our problem instances that we test this on by 85% in most cases. And this approach that we've developed, we've done in a way that we can also use to help us solve other writing type problems, and I'll talk about that at the end as well. So I won't go over this too much, but just as a kind of refresher and a reminder of exactly what the TSP is and how we formulate it as an integer program, the basic idea is that on the right-hand side, we have a depiction of some kind of graph, and this graph has a property that all of the edges in it have some kind of weight associated with it. And what we want to do is take this graph and find a tour in it of least cost. So this might be an example here depicted in the kind of yellowy gold color of the edges that belong to some particular tour. Maybe it's the optimal one. And the edges that are depicted in black are the other edges in this complete graph that don't belong to this tour that we've identified. So when we formulate this as an integer program, typically the way we do it, or one of the easiest ways to do it, is to formulate it using the Danzig, Fuchs, and Johnson integer programming formulation. And for that, what we do is we take each variable or each edge in our graph and associate a variable to it. And in our solution, that variable will take a value of 1 if the associated edge belongs to our solution, and it will take a value of 0 if it doesn't. So that sounds all pretty simple, but what happens is when we try to solve these problems, we have an exponential number of possible solutions that we can come up with in terms of those binary variables. So the more vertices and hence the more edges that we have in our problem, the more difficult it is to solve. And although we have very effective solvers for these particular problems, as they grow, they still get quite difficult for us to solve. So before I move on to how we actually solve them, I'll try and reframe how we actually solve these problems a little bit in a slightly different manner. We can think about the identification of a solution for the TSP as somewhat of a classification problem. So again, we have this graph. The yellowy gold edges are the ones that belong to, let's say, the optimal solution in this case, and the black ones are the ones that don't. We can think of these as a positive class and a negative class. And in the classification problem, that's all we want to do. We want to separate the set of edges that belong to our optimal solution into this positive class and the ones that don't into our negative class. Now, in this case, this would be an extremely difficult optimization problem, because if we try to solve this, classification problem, because we can try to solve it like this, what we want to do is make sure that not only are the correct number of edges in this set n, but also that these edges actually form a feasible tour. So what we're going to do is we're going to still split our optimization problem, or rather the variables of our optimization problem, into two sets, but we're going to take a different approach where we try to remove as many of these as possible, edges as possible, and put them into this set M. But we're not going to look for all of the non-optimal edges, just as many as possible. And the ones that we find are very unlikely to belong to an optimal solution, we'll put in here. And the ones we think that might be likely or somewhat likely to be in an optimal solution, we'll stick them into this set here. So this set might be larger than the set of all optimal, but hopefully every optimal edge and maybe only a small number of the edges that should be in here will be in this set. And then what we'll do is try to solve our problem. So this approach is basically called graph sparsifying, and it's been used in a bunch of other contexts to do similar things for other combinatorial optimization problems. So in particular, what we usually try to do when we solve a problem with integer programming like this is to find the optimal solution from our solution space. So every dot here is indicative of some kind of solution within our solution space, and I'm going to pretend that this is an image of our solution space. And the integer programming approach would get us, hopefully, if we dedicate enough time and resources to it, to our optimal solution. And if we don't want to do that, and we want to maybe take less time to do that, and we're happy enough to get non-optimal solutions, maybe we use a heuristic that gets us solutions in this subset of the solution space here. Our approach is slightly different. What we do is we first cut off this large section of the solution space by fixing these variables, as I'll show. And when we actually go to look for a solution, we have this much smaller space to contend with, and hopefully a much easier time trying to solve our problem. So if I pretend this is a complete graph here, this comes down to looking at our underlying graph for a traveling salesman problem and fixing as many edges as possible. So basically what we do is we just say we no longer are interested in these edges, and we want to look at these edges that are remaining in this new graph and hopefully solve that problem. And this is kind of a bad picture, actually, because this particular case there's actually not any traveling salesman problem tour. There's no TSP or valid TSP tour in there, but the point is that we try to do this. And explicitly what we have to do is for each of our edges, ij, so they go between vertex I and vertex j, we want to construct some kind of feature. And hopefully that feature tells us some useful information about that edge, because we need to have useful information to be able to do our classification. Once we have this feature set. What we want to do is train some kind of supervised learning model. So we want some kind of classifier. Basically, we find an interesting classifier that suits our needs, and get it to output some kind of probability of whether or not that edge belongs to an optimal solution set or not. And that's how we construct M. So M is just the subset of those edges in our original edge set, such that the probability that it, or likelihood, I guess, that it belongs to an optimal set crosses some threshold. Or rather, this is the opposite. What we do is we separate into M those edges that we find with high likelihood are unlikely to belong to our optimal edge set. And obviously then the set of the edges that are likely to belong, or more likely, I should say, to belong to our optimal edge set is just the complement. So when we formulate our optimization problem, or our TSP, using the Danzig, Fuchs, and Johnson formulation, it looks like this. So these are the normal constraints that we have, and the ones that we're interested in particular are these ones outside the box, which still belong to the optimization problem, and these are the integer constraints. Effectively, what we do is just repeat this. We first of all say that these edges, which we know belong to the set of ones that are likely to belong to an optimal solution, we still say they can take values of either 0 or 1, so they're still binary variables, but the variables that we know are unlikely to belong to an optimal solution are fixed to 0. So in a situation where we do well, what we have is this set is much, much smaller than the other set. So we have many, many variables fixed and not that many left to work with. So once we decide that we want to build those features, we have to find out how to actually do that. One of the most obvious ways, and I guess easiest ways to try and build features that tell us something about how likely an edge is to belong to an optimal set is to look at the edge cost, or the edge weight, and compare it to those in its local neighborhood. So we might take, for example, well, we'll do this for every edge in the graph, but we'll just look at this one, for example, the edge that goes between A and B. We have some variable associated with that. We designate with x sub AB. And what we do is we take this edge and compare its weight with those in its neighborhood, maybe those incident with B. So these green ones here, we compare to these. And maybe it's just something as simple as a division, and we normalize that somehow. And we might compare that with those of the neighborhood on the opposite side as well. So those incident with A. And we might also take that edge weight and compare it with some global properties of our graph, which might be described by, for example, something like the maximum edge weight that we see in our graph, or maybe the mean or the minimum edge weight. And that should hopefully give us a good idea of what these edges look like in comparison to the rest of the graph, and that should help us to discriminate them a little bit. But it's obviously not enough, because if that was enough to solve our problem, then this would have been figured out a long time ago, and we'd be able to solve our TSP without that much trouble. So we have to construct something a little bit more complex in this to make our discrimination a little bit more effective. So one of the features that we build it's pretty much influenced and kind of inspired by the fact that for a lot of, or for two of the, I guess, the main approximation algorithms that we use for symmetric Euclidean TSPs, we have to construct minimum spanning trees. And they tell us interesting things about the properties of our graph. So basically, to construct these features, all we do is we look at our graph, and again, just for the purpose of this presentation, I'm going to pretend that this is a complete graph, and we compute a minimum spanning tree. So we find the edges that belong to this tree here, and then what we do is we construct a new graph as well, and this graph has the exact same vertices as the original graph, but none of the edges. And what we're going to do is, once we've computed that first tree, we take the edges that are in this tree and place them into our new graph. And we'll repeat this process, but only after we remove these edges from the original tree. So we remove them from the original graph, I should say, and then we compute a new minimum weight spanning tree. And we repeatedly do this, so we've reached some kind of computational budget that we're happy with. And what we end up with is a graph on the right-hand side with much fewer edges, hopefully, than the one on the left. But those edges should tell us a good bit about the structure of our graph. And what we'll do is, once we put them into our graph on the right-hand side, depending on the order in which they go in, we'll weight them accordingly. And that will tell us something about how important they were, at least relative to each other as well. So what we can do as well is build features by solving slightly easier problems, or, well, significantly easier problems on the TSP. So again, this image on the left is just for purposes of demonstration. It kind of depicts an integer programming problem where we know the solution already. It's this purple X we have in the middle, and maybe we have some constraints that are known. And a typical way to make these kind of problems easier to solve is to do some kind of relaxation. And one of the easiest ones we can do is a linear relaxation, where we just drop the integrality constraints on our binary variables and we solve our problem. And we might get something that looks like this this green dot here. And hopefully that might tell us something about our optimization problem and the structure of that optimization problem. Now, if we use the Danzig, Focus, and Johnson formulation of our integer programming problem for the TSP in particular, it's known that this can be quite far away from our optimal solution. So it's not likely it'll be telling us a whole lot about our problem. So rather than just take the information we get from the solution, which would be non-integer values for all of the different variables, what we'll do is do something slightly better. We'll solve this once. This will be the initial node in the branch and bound tree. And we'll look at the solution and inspect it. And maybe we see that we can add in some sub-tour elimination constraints. And in fact, maybe we might even have the optimal solution. And that does happen in some cases. And if we do, we can just stop right there. We don't need to do any more when we've solved the problem. But if we don't, then we can keep doing this process again until we reach some kind of computational budget. So we might add in several cuts. Hopefully something in a process that's not too expensive. And when we're satisfied that we've done this enough times, we'll look at this solution here, which again will hopefully have non-zero values for quite a few of the variables in our optimization problem. And hopefully those values tell us something about what the structure of our optimization problem is, and hopefully how likely each of those individual edges associated with those variables are to be involved in an optimal solution. And if we wanted to have more non-zeros in this feature as well, instead of maybe taking the solution to this easier problem, what we might do is just take the reduced costs and normalize them. So these features, once we construct them, theoretically allow us to solve our problem. So what we can do is construct our feature set based off the features I just described, train some kind of model, assuming that we know which edges belong to the optimal set and which don't for this training set that we assume that we have. And then we use our classifier to sparsify our graphs, to remove as many variables as possible, and then hopefully we have something that looks nice. Except there's one more thing that we have to take into account, and that's making sure that once we actually do this, that our graphs look right. And by that I mean, when we have a TSP, it's actually common enough that we can have several optimal solutions. So maybe we have a TSP like this graph here on the left, and we have this optimal solution depicted here in, again, yellow and kind of gold. Perhaps that's one solution, and perhaps we have another one that looks a bit like this. So if we actually look at the optimal solution set, we see that it's a little bit bigger than just the minimum number required to make a tour. And what we want to do is, in an ideal scenario, sparsify the graph with our just trained classifier that we trained using our features just now to look like this. So we remove only the black edges, the ones that don't belong to any optimal solutions, and then when we try to solve this, we have an easy time and nothing's too difficult anymore. But in practice, that's not what happens. What actually happens is something closer to this. And this is a really extreme case where we've removed a lot of the edges, and we've removed quite a few of the optimal edges, and we've removed quite a few of the non-optimal edges. But unfortunately, when we remove them like this, we've actually created a situation where the resulting problem that we would solve is not a feasible problem. So we can't get a feasible tour here, even if it's far from optimal. So a way we can fix that really easily, because if we wanted to check that we can't have a tour here, that itself is a difficult optimization problem. What we can instead do is look for a tour that we do know and insert it into the graph. So it doesn't even have to be a good tour. As long as we insert any tour into this graph, what we can do is guarantee that there is a solution that we can find here, and that solution might actually be better than the one we provide, depending on the edges that were left behind in the graph. If we do this with an approximation algorithm, that's how we provide bounds to the quality of our optimal solution. So as long as we have an approximate solution with known bounds on its optimality, then we also have known bounds on the optimality of the resulting proven problem instance. So we can make some guarantees about the quality of the solution that we can get once we do all this work. If we don't have access to nice approximation algorithms, we can instead insert random tours if we can do that, or even just ones that we get from a heuristic. So usually we can guarantee some level of quality with these kind of solutions, these kind of pruned instances. So that's the kind of general idea about how we go and do this. But then in practice, I guess it's the more interesting part. So the first thing that we focus on is that we have relatively small data sets. So like I said in the previous slide, what we might have is a situation where for each of our TSP instances that we want to look at, we have several optimal solutions. And again, the problem here that we're trying to solve is one where we classify the set of non-optimal edges from optimal edges, those edges that never belonged to an optimal solution to those that do belong to an optimal solution. So that means we have to solve our TSPs several times to get the labels which tell us which edges belong to those sets or not, because we might need to get several optimal solutions. So if we're going to get label data, we need to make sure that we can actually do it in a reasonable amount of time. So to do that, obviously our ability to do that again is not only limited by the fact that we have several problems to solve several times, but also the problems themselves might be extremely difficult. So what we're going to do is focus on a benchmark set that we know is small and that we know the problems aren't tremendously difficult to solve. And we'll hope that once we do that, we can generalize well to a setting where we have more difficult problem instances and hopefully larger problem instances. So the benchmark set that we rely on is the Matilda instances. So here we have 7 classes of 190 instances each, but thankfully they're only 100 city problems. So that means there are 100 vertices in each one. And for something like Concord, the Concord solver, these are extremely easy to solve, at least for the most part. And what we'll do is only train on the difficult benchmark instances within that problem set. So some of them are known to be more difficult than others. And from our own experimentation and from indications from other works, we've seen that actually training on these instances leads to better generalization later on. So we don't even train on the entire set that we have here. Then when we do testing, we test them on the more famous TSP-lib instance set. So these range from 17 vertices to much more than this. I think it's 89,000 vertex problems. We test our instances or our classifier instances between 17 and 4,432 cities or vertices, and these have vastly different distributions of weights than the training set. So the training sets are basically generated using random generation techniques. These vary from strikingly similar ones to geographic problems to drilling problems, which have a very regular structure, which are completely different, and they do pose a problem for these kind of approaches to solve. And of course, since we add these 3 extra steps to solving our optimization problem, we need to make sure they're all quick. So we need to make sure that the features we compute are cheap, which we've done. We need to make sure that when we train the models, that when we do inference, that's quick, because we have to do inference for every single edge independently, which could be a very large number, especially if the graph is huge. And also, we need to make sure that when we do the feasibilities checks, we need to use quick algorithms that help us get quick solutions. So in this case, for the TSP, the Christofides and the double tree approximation algorithms are nice and quick, and we can use them to get us to a somewhat reasonable and guaranteed value on our optimization problems, optimal objective, once we reduce it. Okay, so
James,
that's...
sorry. James, 1 minute left. Yeah, if you can be quick in 1 minute, so yeah.
Yep, okay. So I will skip ahead then 2 slides. So basically, the main thing we want to show is that when we use this to solve, or when we use this to reduce our optimization problems, in particular for the TSP-lib dataset, we see that when we do that, actually in 92% of cases, we have an optimal objective in the pruned instance. So that is the optimality, the optimal objective value of the pruned instance divided by the optimal objective value of the original instance, which means that we made the problem easier to solve, but didn't lose any optimality in doing so. And in the worst case, we go above about 10% away from the original optimal solution. But in general, the performance tends to be quite good. And we use relatively simple models, again, just a linear support vector machine and a logistic regression. Let's skip ahead. We can do that with pruning rates. Basically, the number of variables we reduce up to 94% in the Matilda problem instances, and almost up to 95% in the TSP-lib problem instances. So I'll skip ahead and just try and plot that, just so that when we plot the order of the problems, this is the size of the problem instance against the pruning rate. We see that Generally, the larger the problem is, the more edges we can remove, and the colors indicate how far we are from optimality, so the bluer they are, the better. And there's no real relationship between the size of the problem and the optimality that we get. So the larger the problem is, or for large problems, this tends to generalize well, which is the main concern, because with deep learning methods in particular, which have been used to solve the TSP, we get very poor generalization as the problem size grows. Just let me just summarize, I guess, but where we would like to go next is to improve the feature computation to make it a little bit more efficient, leverage multi-stage sparsification. So rather do this in one step, sparsify a little bit each time, and hopefully make this cost a little bit less in terms of computation, and also get us better performance in terms of the optimality ratio and the actual number of variables that we remove. We want to integrate branch and cut features that are hopefully a little bit more expressive. Most important thing of all is develop this approach further for vehicle routing problems where the utility will be greatest, and we don't have solvers like Concord that can help us solve these problems really quickly. So we want to use it to try and increase the utility of vehicle routing problems posed as 2-index integer programming problems. Okay, sorry I rushed through that, but that's it, and thank you.
Okay, thank you very much, James, for your talk. And well, we have now some time for questions for any of the three speakers. If you want to ask something, you can type it on the chat or maybe raise your hand and I give you permission to unmute yourself and put your camera on if you want.
Can I break the ice? Oh, there is a question actually. So
okay.
It's a question to James. How do you handle the different dimensions of the graph in your machine learning model?
Janice, if you want to ask.
Yes, hello, can you hear me?
Yes, great.
Yes.
Perfect. Thanks. So maybe I missed it, but so you can have, if you train your model on a small graph, then somehow you want to solve the same problem on larger graphs. So how do you adjust your model, or do you predict each edge by its own?
Yes, this is one of the things that possibly could be improved in further iterations, but at the moment each edge is predicted independently, so that's why we rely on very simple models, or at least ones that have relatively simple inference techniques to do this for us, because if we have to predict for a large number of edges for maybe something like graphs with 10,000 or more nodes, that means we have a lot of time dedicated to inference. So each edge is computed independently, and the feature representation size should always be the same. It just means we dedicate more time to doing the inference.
Okay, thank you.
Can I ask Manuel about his presentation? So my question is, I don't know, because in the end, I realized that you have only one explanatory variable, but in general, how do you think is it possible to apply a method for autoregressive process when your explanatory variable is a log of your response, for example?
Yes, you can take the continuous variable you want. So if you take the logarithm of your variable, you can have this as a predictor variable. No, you will take the logarithm of the response variable, I think. So,
yeah, it's not logarithm, it's log. It means that we consider past observations, like 1 year ago, for predict current response.
Yeah, the examples I used are time series, but you can do backwards prediction, extending the BS plan basis on the other side. I just use the forward prediction because I think it's more intuitive, but the methodology is the same in both questions.
Okay, great. Thank you.
Okay, are there any more questions?
Actually, I have one question to Remy. My question is, because I see that you can reduce the granularity of the hierarchical categorical variables, but what if you apply this approach? So you build this tree based on the continuous variable, for example, age, and then you can, in the end, choose, let's say, more informative age groups or so. How do you
Yeah,
think can it
yeah,
work?
I see your point. Yeah, in fact, we have an example of working with continuous variable, and we try to split it like greater than the mean, or like a value less, smaller than the mean or something like that, and try to apply this methodology to other kind of variables. Yeah, we can work with a continuous variable, but we have to discretize the variable.
Yeah, so you mean that
Yeah.
if you use all possible values of this continuous variable, then the tree could be very deep, or like. So it's also the question how to build this tree in advance, right? How?
Yeah. Well, you mean in continuous variable?
Yeah.
Yeah, we have worked with only 2 levels, like try to perform a small tree, because maybe if we want to know if only need information like if the value is greater or not than the mean, for instance, maybe with such information you can get a good prediction, but we don't have very complicated example in such sense. But it's true that it can be applied for continuous variable if we discretize them. Yeah.
Okay, thank you. Thank you very much for your reply.
Thanks.
Do we have any more questions? Okay, Paula. Now you should be able to unmute yourself, Paula.
Excellent. Hopefully you can hear me.
Yes.
Great. Yes.
Excellent. Quick question for Emmanuel. Thank you. That was a lovely, interesting presentation. If I understand correctly, you had a constraint on the ordinality, the number of features or explanatory variables that are selected. So you call that the complexity?
Yeah, but we use that term when we talk about hierarchical categorical variables. Then, if, for instance, if we want to consider a sparse solution also in the other variables, in continuous and categorical variables, we can use, for instance, the lasso objective function and try to get more sparse solution. But when we use complexity is when we deal with hierarchical categorical variables. But if we want to add the other sparsity, like the other one, we can try to include that in the objective function.
Mm-hmm. Yeah, good. Thank you. Yeah, very interesting. Thank you.
Thanks. Thank you.
Thank you, Paula. Do we have more questions from the audience? Okay, so if it is not the case, we have to say not goodbye, but see you next week for another talk with Tias Gans. Thank you for everybody, for the speakers, the audience. See you.
Thank you very much.
Thank
Thanks.
you. Thank you to the speakers. Thank you so much.